All right, we are on the home stretch of our last chapter here. So, we've talked about forces and Newton's laws and how they drive a lot of the motion and forces in the world around us. The last thing that we usually kind of throw into this chapter, and it does belong here, is called potential and kinetic energy. And it's just another manipulation of how things are moving and the forces that play in the world. So, just to kind of give you a little background, we scientifically define energy as the ability to do work. We know that there's all different kinds of energy in the world. There's chemical energy of the food in our bodies. There's electrical energy that makes our appliances go. And then we're going to talk about a few other specific ones as we go here. But it is important. One of the driving things we need to remember is that energy, we have a set amount of energy in the universe. We can't create or destroy it, meaning that it's always conserved. But we can change the form that it's in. So energy can be transferred or transformed into different kinds. But the amount of energy stays constant. So specifically in our chapter here, we're going to just really quick explore two types of energy. They're called potential and kinetic energy. Okay, so potential, a lot of times when you hear about potential, you think about, oh, this kid has a lot of potential to be a good baseball player. And that's kind of can relate to this. We call it usually the energy of position because the position it's in has the ability to do work if it changes. So the main type we'll talk about in our class is called gravitational potential energy. There's also elastic potential energy, like if I take a rubber band and I stretch it out, it has potential energy stored because of the position I'm holding that rubber band in. But when we talk about gravitational potential energy, it depends on the mass of the object. So if I hold a bowling ball and a ping pong ball above your head, they obviously have different amounts of energy, and the height of that object, meaning if I hold a pencil 1 foot above the ground or 10 feet above the ground, it has different amounts of energy there. So the way that we calculate it is m times g times h for potential energy. This is the mass. G stands for gravity. We know on Earth that that's right around 10 meters per second per second. And again, there's the height. So the higher up I hold something, the more energy it has, and that makes sense because as it falls, we know that it will speed up. And then again, the mass is important just because heavier objects can do more work. So a lot of times, like I mentioned, we do call this stored energy because of its position. The other type is called kinetic energy. And if you think about a kinesiologist, what a kinesiologist studies is people moving. And that's really what kinetic energy is all about. It's the energy of motion. Remember, we talked about kinetic energy with temperature. It's how fast particles are moving. It's motion again. So it depends on mass and velocity. So again, if I threw a bowling ball at you and threw a ping pong ball at you, the mass of that object is definitely going to affect how much work it does on your body. But here the velocity is also important. And this makes sense because if I hit you with a baseball that's thrown 30 miles an hour versus 90 miles an hour, we know that the amount of work translated is definitely dependent on velocity. So how you calculate this, and we won't probably have any complex ones of these, but it's 1/2 m times v squared, where m stands for the mass and v stands for the velocity. And you can see how the velocity component is squared, showing that it influences the kinetic energy the most. The mass is still very important, but you can see how this is all about the energy of motion because we're measuring how fast are those things moving. Now remember, we just said energy is always conserved, so this little yo-yo pendulum, the thing you have to understand is that up here, it has 30, we measure it in joules usually, but let's just say it has 30 joules of energy. Right here, it's a different form, but it has 30 joules of energy. And all the way up here, it's different forms, but it still has 30 total joules of energy. And this infographic is really, really nice. It just shows how all the way up here, when you take that pendulum and you bring it back, it's not moving. So it has no potential energy. It's at rest. Excuse me. It has no kinetic energy. It's all potential energy, but as it falls, the height gets lower. So somewhere in here, we're losing potential energy, but since it's picking up speed, it's gaining kinetic energy. And at the very, very bottom of the pendulum here, we know that it's the lowest. So down here, it doesn't have any potential energy, but it's moving the fastest. So this right here would have 30 joules and it'd all be kinetic energy, whereas up here it's 30 joules and it's all potential energy because it's not moving and it's high up. As it approaches that pendulum though and comes back up to the other side here, it starts to slow down, which is why our kinetic energy goes away and it's getting higher, storing more energy in the form of potential energy. So Somewhere in the middle here, it's probably a mixture of 15 joules kinetic energy and 15 joules potential energy. But at the highest points, it's all potential, and at the lowest points, where it's going the fastest, it has the most kinetic energy. You'll have a little problem about a roller coaster, and that's where a lot of this idea of conserving energy comes into play. Good luck on your quiz. Look over the chapter if you need to.